Thanks, Rick, and great to be back here. Idaho National Laboratory, if you're not familiar with it, is in fact one of the 17 national laboratories for the Department of Energy complex. We're known as the nation's nuclear laboratory, but that's not the part I work at. I actually learned more about small modular reactors than I ever knew from the last 20 minutes listening to Bob, which was awesome. I work in the National and Homeland Security portion of the lab, and the portfolios that I support most of the time are energy cybersecurity. And energy security in and of itself, simply having that reliable, safe power, sustainable power, is an element of national security. I could go on for a long time, talking about this philosophy, but catch me afterwards if you want to do that. What I want to talk about here quickly is some more complexity to this, because hearing Neil Chatterjee talk about the policy complexity, and that's real, don't underestimate it. There's a whole dimension of technical complexity that goes with this also. Rick also used this slide, but it basically shows the flow of raw energy sources, not truly raw energy sources, through the actual consumption of it. And you can see what it was last year, and it's changing and it's evolving. You can see that the coal line shrinks year over year. What you're also going to see, though, is electricity is growing. We are on a trend to electrify all the things. Transportation might be the single largest one of those. I know there's a lot of vendors here that are looking at some of the major investments that are going to be required for that. It's not just the use of the transportation itself, but also the supporting system of systems to get to that step change right there. So this is going to shift a lot. The other thing that I want to mention from this chart that it caught my attention, but then I had to think back to my physics classes, basic science, and remember it, is the efficiency of this. Only about a third of the energy that we actually start with gets put to a productive use at the end. And there's some fundamental physics to this that create these limits. So we're not ever going to be able to say, well, let's get it up to 95%, let's get up to 99%. That's not the way that the world we live in works. But the point is that being able to control at the largest scales our use of energy, that could be efficiency, that could be smart choices, that could be co-generation, but a co-use sort of perspective as well. Those things are all at play in this. And it's going to be a portfolio solution, right? The Obama administration said it was a portfolio of everything. It's all on the table as far as our generation sources, and I think that's really what it is. I'm a nuclear fan. I came out of traditional power delivery. I think there is probably a role to play for everything, but it's not necessarily one that is going to be the same role for all the different sources. But no matter what the source is, and this is where I kind of stop talking about differences between the sources and talk about what do they all need to provide at some level, and they're all different, right? Because each one of these energy sources and their technologies are going to give you different amounts and different capabilities, and they're going to come with different constraints and requirements. But they're all going to have some things in common. Number one is that they're all going to interconnect to our transmission and distribution grid, the power delivery system. And the traditional view of this, I actually built this infographic, which is why the quality is terrible. So please forgive me that. And if you're a graphic designer, talk to me afterwards. If you think of the traditional mental model and the graphic that's used from FERC, from NERC, from the Department of Energy even, it's very linear. You've got generation on one side, goes to transmission, to distribution, and then to some houses and factories. And that's not incorrect from a power flow perspective, but it masks a lot of complexity that's very important in it, is that really it behaves like a cloud. I think the pointer's not working, that's fine. You can see I redrew the transmission system, the bulk electric system more properly, as kind of a cloud. We're talking about digitalization here at ARC at this conference. And this notion that there's some similarities from the bulk electric system that is densely interconnected, it is redundant, it is highly resilient. The one other thing we have on the electrical side that isn't there in the IT clouds at this point is a high degree of regulation. There's some good things about it, there's some painful things about it, but it is what it is. Below that, you have got these series parallel chains that interconnect that dense network getting down closer to the load. This is sub-transmission starting to get into distribution. There's a lot of debate over where the exact lines are for the words. I'm less concerned about that, except to note that it comes out of this it takes a licking and keeps on ticking, very dense interconnection, and then starts having these chains that come off it. And then to where it gets down to the actual end use customers at the end, eventually going down to some radial connection for the last mile, 100 feet, 100 miles, depending on your situation. And in the last 15 or so years, we've also seen the emergence of distributed energy resources, these DERs, that plug in where they fit. A lot of times this is actually behind the meter at residences, at industrial complexes. Some of them plug to the distribution system, some of them even at sub-transmission. When I worked at NERC for a couple of years, it was interesting to watch some of the, I'll call it strategy and not game playing, of saying, okay, let's make sure that we stay just outside the stretch of regulation for where we're getting interconnected to site some of these things. And this is also sort of conceptual. The issue of physically siting this infrastructure to be able, for whatever the new generation mix is, whatever it evolves to get it to wherever the loads are. Because guess what? People move around. Population shift, not just from year to year, and you look at a lot of the things you can see on the internet about how states are gaining or losing populations. But think about climate change. And over the next 100 years, what population shifts that's going to cause. This is all steel on the ground. So we need to be skating to where the puck is, to quote Wayne Gretzky, and saying, how do we make sure that we have the energy available where it's going to be needed for where the humans are going to be at the time we get it built. Gets to be kind of a complex problem. The next one I want to talk about, this is where it gets the most technical, but it's not just, and it's also where I got the title for the presentation. It's not just the megawatts. And I'm not saying that, we need to bring all this into every discussion. No, we don't, because megawatts is the fundamental quantity by which we measure electrical energy. So I'm not fighting that at all. However, when we talk about it, because the words we use and what we listen to and hear and understand, it has some implicit influence on our mental models. And we are at peril if we don't remember, or at least trust that the appropriate folks that are doing the design and the planning and the construction and the policy do remember that it's not just megawatts. There are other things that you need to have to keep that complicated, complex grid system working all the time. So you need the megawatts to be able to serve the load, but along with that, you need inertia. You need voltage control, which is related to reactive power. You need active power control, which is what you need to move your loads up and down to be able to match whatever your net demand is, which is time variant, both intraday, weekly, seasonal, day of week, any number of different dimensions there. You need to be able to do it at a speed that matches what the load is changing for. And of course, you can play with the load side too. You can curtail things. We were having a discussion before where you can do things with the generation like the SMRs use, that we don't like to reject generation, but you can just blow off steam and use that as a way to be able to gain or speed the rate at which you ramp. It's not the most efficient in the biggest picture, but it might be the right choice in some cases. You need to have reserves also. And when we talk about we're going to replace conventional old dirty coal generation, there's 5,000 megawatts that are retiring. We're going to replace it with 5,000 megawatts of clean solar, wind, whatever inverter-based generation technology you like. A one-for-one is not going to get nearly close enough to what we need to actually operate the grid, because you need to have reserves. You need to have margin for the imposition of your load forecasts. You need to have margin for being able to withstand the loss of other generating units. That largest unit that's on your system, if it were to trip, because guess what? Technology fails. We know this. You need to be able to have the grid maintain its stability and be able to replace that both in the real time and then by redispatch to be able to make up for that lost resource until it's able to come back on some period of minutes or hours or maybe days or weeks later. You need to be able to ride through disturbances on the transmission system. And this is interesting. I didn't plan this, believe me, but June 4th, out in Texas, there was the largest loss of inverter-based resources that we have ever seen in North America following a transmission disturbance. It happened June 4th. There's not a lot of public details about it, but because ERCOT is an ISO, they have some transparency rules, that there was a posting on it. And I saw it, my friends at NERC saw it, and there's going to be a big report on it. 2,365 megawatts of inverter-based resources were lost in less than 1 minute. It was probably about 10 seconds as the result of an incident that I know a little bit about. But what I will say is that it was a transmission system disturbance. Something happened on the transmission system, knocked out a whole bunch of distributed resources, inverter-based resources that were not connected to it. And I see some curious looks in the audience. This is not the first time it's happened, not the second, probably about the 9th or 10th. This goes back to 2016 with the Blue Cut fire in California, where transmission that had tripped because of wildfires caused enough of a voltage sag on the transmission system that all these inverter-based resources saw that voltage sag, and they did what they were designed to do at the time they were installed. Block, trip off, wait 5 minutes, and then attempt a restart, which years ago when they were designed and installed, that was the way we operated the system. But they're still in service, but the penetration of inverter-based resources has gotten so great since then that now, we don't want them to get out of the way and we'll restore the system and tell you when to come back on. We need them to stay on, ride through disturbances in real time to provide the same sort of stability that we would used to get from the traditional rotating mass, the large fossil-fired plants and nuclear plants. This is changing. It's getting worse. We know a lot of the technological solutions to do it, but like many things, it comes down to the policy and the economics. These are distributed, so in many cases, it's touch labor to go out to every single inverter and make updating changes to the firmware for how it behaves in response to conditions that nobody thought of when they designed it. It's not a mistake. It's not a bad design. We learned. And in many cases, you can't even make these changes. So we'll have to wait until those types of inverters age out, and then we'll have to replace them. The important takeaway from that is let's build the stuff that we're building now, right, with all the best insights that we have and the flexibility to be able to make these kind of changes that we know are coming, even though we can't necessarily anticipate the particulars of what they all are. And the last one here that gets very little mention, but if you have all these resources that are distributed all over the place and you have these expectations of them in your operational plan and context to be able to do certain things, there's basically two ways that you can do it. Is one, you can make it autonomous, that it responds to the signals that it comes in from the voltage frequency of the grid, and we do that to a certain extent, but you also need communications with it to be able to control it. This is for setting its output, placing it in different modes, potentially maintenance issues, depending on how you want to do it, certainly visibility of what it's doing, so you can get the data back to it and use that into your larger energy management systems. And this is where I put this phrase consequence aligned in there. One of the things that we do at the lab a lot is look at consequences, and we use that to drive our decisions with risk and cybersecurity. So given that particular resource, this is not a one-size-fits-all solution. How reliable does it need to be? What's the latency? You know, how redundant? What sort of bandwidth? How big a pipe are we talking from the communications? And security. I would get many dirty stares from my coworkers if I didn't put cybersecurity top of the list, but not everything has to be the absolute top tier of security. We couldn't afford that. We have to be thinking of this and making a conscious, deliberate business decision when we build the security in. And that needs to be a part of it, yes. And thankfully, that brings me to the last thing, is that we need governance for all this. And it needs to last from sub-cycle electric to generational.